today we're going to take notes on a few different topics that I've just kind of grouped all together on one slideshow. So we're going to take notes, and so there isn't one big overarching category, but we're just going to talk a little bit more about covalent bonding and a little bit about metallic bonding and a little bit about alloys. So that's going to be kind of some different vocabulary that we're going to cover today. And what I have for you, I want you to copy the red. So I'll give you time to do that. I know. At least it's not my bad handwriting. Oh, we lost somebody. So this is something that I kept telling you we're going to learn about later this week. We're going to learn about later this week. So here we are. It's the last day of the week. Diatomic elements. Diatomic elements that bond to another atom of the same of itself when it is a gas. And there's 7 diatomic elements, and their names are Hunkelbreth or Brinkelhoff, and then you can remember all the 7 elements. It's also kind of easy to spot them because they make a 7 on the periodic table plus hydrogen. So if you look at the periodic table, everyone find nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and then hydrogen. Those are the 7 diatomic elements. So it's hydrogen plus the 7 gases on the periodic table. So when those elements are gases, they bond to each other. And so you're not going to find just O. You're always going to find O2. You're not going to find N gas. You're always going to find N2 gas. You're not going to find chlorine gas. It's always Cl2 gas. And so when those are gases, they always bond to each other, and you always have 2. So diatomic means 2 atoms stuck together. And that's why we can call them oxygen, or we can call it oxygen gas, and it means the exact same thing because there's no such thing as just O floating around. It doesn't happen. So remember when we were doing naming earlier this week and we had like just F2 and I said, oh, that's just fluorine. It's because it's one of the 7 diatomic elements. So hopefully when you're writing Hunkelbreth, you're being careful with that L and that R and drawing them as lowercase letters because those are the 7 symbols of the 7 diatomic elements. So what would the chemical formula be of chlorine if I say I have chlorine gas? Cl2. What would the chemical formula be of iodine if I said I have iodine gas? What would the chemical formula be of krypton if I say I have krypton gas? Just Kr. It doesn't react, it's a noble gas. So the only ones that you put a 2 after are Hunkelbrief: hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. So again, it makes a 7 at the periodic table, starting at element number 7. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Those are the 7 elements for Hunkelbrief. So any other element, if it's in a gas form, it's just by itself. It's just 1. The 7 diatomic elements are those 7. Sound good? And again, your notes are always available for you for quizzes and tests, so that should be a good thing. Next topic. I think I'm going to be quick today. Give you some time for me to bug you about missing work. Our next topic is metallic bonding. Does anyone remember the characteristics we learned about metals? If an element is a metal, we learned 4 different characteristics about it. Metals are shiny or have luster. Yeah, what else? Metals are malleable, which means they can be pounded or bent and hold that new shape. They're good conductors of heat and electricity. And they're ductile. They can be made into long, skinny wires. All of these are because of a characteristic of metals that we call metallic bonding. Bonding is sort of a stretch as far as a term because it's not bonding to anything else, but it is becoming stable. So remember when we learned ionic bonding and we learned that metals lose electrons to become stable, non-metals gain electrons to become stable in ionic bonding. So metals are on the left side of the periodic table. They typically have 1, 2, or 3 valence electrons, so they lose 1, 2, or 3 electrons, and then the next layer is stable. Remember us talking about that? And so when you have a chunk of metal, let's say I have a chunk of aluminum, it's not all aluminum. What it ends up doing is all the aluminum atoms give away their electrons, and they all become aluminum plus 3, and then there's extra electrons floating around. So do you see in this picture how they show like a positive circle? That's supposed to be the aluminum atom. And then it shows all those extra dots. Those would be like the electrons that it has released. And so in metallic bonding, a metal gives away electrons to become stable. And so there's just a whole bunch of electrons flowing around outside. So electricity is the flow of electrons. Does it make sense that if a metal has released a bunch of electrons that it's no longer holding on to, that they could flow? Does that kind of make sense? They're not being held on to by the atom anymore, right? Those valence electrons have been released. The flowing electrons are actually what reflects light and makes metal shiny. So the reason metals are shiny is because those extra electrons that they release reflect light. That's also why they are malleable and ductile. Because have you ever seen that scene? Of course you have, in Home Alone, where the bad guys are there and they like throw the marbles and the guys start slipping and tripping and they can't make contact with the ground because the marbles are rolling? That's kind of what electrons are like at the atomic level. So there's atoms and then there's all these little electrons, and when you pound a piece of metal with a hammer, the atoms kind of slide past each other because there's those slippery electrons in between. Does that kind of make sense? That's why metals are malleable and they aren't going to break the way a non-metal is. A non-metal is brittle. If you hit it, it just cracks. Metals, if you hit it, it dents or it bends or it moves because those atoms can kind of slide past each other. And the reason they can is because of the sea of electrons surrounding it. That's also why they are ductile. And so if you have a pure metal, chances are you actually have pure metal ions with a whole bunch of extra electrons that have been released. They can conduct electricity, they can reflect light, they can allow it to be malleable and ductile. And so that's what you need to know about metallic bonding. Questions on that? Kind of a weird concept. They're not necessarily bonding with anything else, but they are becoming stable, and that sea of electrons gives metals their properties. I don't want you to write this down. I just said it. But I don't want you to write that many words. So it says a metal crystal consists of positively charged ions in a sea of valence electrons. They can be reflective. They can be a good conductor, malleable, and ductile because of that sea of electrons. So this slideshow will be posted. I don't think you need to write down all those words. Next term, alloy. So an alloy is not a chemical bond. It is literally a mixture. And so it's if we've taken a bunch of elements and kind of melted them together to mix them up, but we haven't actually bonded them. They're just mixed together. Just like if you take ingredients of a salad and mix them up, we're taking atoms, we're kind of melting them together so they mix up, but they're still individual atoms. They're not bonded or anything like that. So an alloy is a mixture of two or more elements. At least one of the elements has to be a metal in order for it to be called an alloy. And the cool thing about alloys is that if you mix two or more elements, not bonding them, because bonding can completely change the characteristics, but if you mix them, the characteristic of the mixture is a combination of the characteristics of the substance that you mixed. And we have two types of alloys, and I want you to listen first, and then I'll give you time to write this down, because I do want you to listen, and I will keep this slide up for you. But the first type of alloy is called a substitutional alloy. And a substitutional alloy is sort of like this picture here, where do you see how we have this kind of blue circle atom and we have this gold circle atom? They're not exactly the same size, but they're close. And in a substitutional alloy, we mix two or more things that are similar in size. And so what happens visually is you see a mixture of the two colors. So like brass, does anyone know what elements brass is made out of? Does everyone know what brass looks like? What does it look like? What color does it look like? Gold, right? So brass is like the brass instruments, the gold instruments in the band. Now they're not made of gold, they're made of brass. And brass is a mixture of two elements that are similar in size. It is copper, which is, we all know what copper, like penny colored, and zinc, which is silver. And when you mix copper and zinc, a coppery color and a silvery color, it actually to our eyes looks bright, shiny gold. That's what brass is. And so what happens is you've got a bunch of copper atoms that are similar size to zinc atoms. They kind of line up copper, zinc, copper, zinc, copper, zinc. And so to our eyes, we see a mixture of the two and we interpret that as a gold color. So that's what brass is. It's just a mixture of those two colors to give the shiny, that new color. The other type of alloy is an interstitial alloy. And you've definitely heard of examples of these before. This is the picture B. In an interstitial alloy, you have a big element and you have an element that's much, much smaller. And typically what it does is it fills in the gaps and makes it stronger. And so some examples of interstitial alloys are steel. Have you heard of that steel? What is steel made of? Do you know? Steel always has iron in it, and then it has a mixture of other elements. And it makes it a stronger metal, a stronger mixture than any of the individual elements. And so it has iron and it fills in the cracks of that iron with other elements and it makes it stronger because if there's gaps, they can slide a little. If the gaps are full, it's more packed tight. And so there's different mixtures of steel for different strengths and different things, but steel is an example of an interstitial alloy. That smaller one you can't see because it's so tiny, but it adds strength. Another example of an interstitial alloy is gold. And if you're ever going to buy any kind of nice jewelry one day, you want to understand the difference, okay? 14 karat gold and 24 karat gold have different price points. Which one's more expensive? 24 karat gold. It's more pure. It has more gold and less other things. And FYI, gold is soft. Gold is a soft metal that isn't very strong. 24 karat gold is good for like earrings and maybe like delicate small necklaces. You don't want a 24 karat gold bracelet or watch or ring or anything like that because they will lose shape. They will literally change form because rings and things like that get banged around. They bump into things. You don't want a soft gold to make a ring. It's going to literally change shape. What you want for a ring is something more like 14 karat gold. It still looks just as gold as 24 karat gold, but it has more stuff filling in the cracks. So it's literally stronger and will last longer and hold its shape. It's also cheaper. So that's an interesting one. Some people assume, oh, well, the more expensive one is better and going to last longer. And the thing is, at some jewelry stores, they'll sell you things in 24 karat that really shouldn't be 24 karat as far as longevity and lasting. And so this is an interstitial alloy. It's not visibly going to look any golder if it's 24 karat gold or 14 karat gold. You're still only seeing the gold. But if it's 14 karat gold, it has more things like this filling in the cracks, which means it's stronger and it's going to last longer. So that's always something interesting that I think people don't realize when they make those kinds of purchases. Yes, sir. It's not going to be easy to bend a gold bar because that is a 80-pound, very dense, thick thing. But when we're talking about making gold into a narrow jewelry link for a chain or something like that, then it is a softer metal than other metals. It's still not like crazy soft. Like you probably can't use your fingernail and indent it, but if you bang it a bunch over time, it will distort. And so 14 karat gold is less likely to do that than 24 karat gold. Does that answer your question? Yeah, and so it's not like Play-Doh soft. It's just softer metal. Yeah, but it's also one of the most dense. And so it's very unique in that characteristic as well. It's very heavy. A block of gold this big weighs like 80 pounds, which is a lot of weight in a very small space. And that's actually it for our notes for today. So I thought we'd end early on this Friday. And if I have any people in my classroom with missing assignments, I'm going to have them work on those. And if any of you at home are owing me missing assignments, now is some bonus time to get working on that. And then I will see you guys on Monday.